All right. Hey, everybody. Thanks for joining us for the pre-show. Just like we did last week, we're going to cover some of the latest stories in cyber news before we get going with the actual class at 10 o'clock. So if you're here for the pre-show, welcome. If not, I guess not welcome. You're not here to hear this anyway. So let's talk a little bit about some cyber news. We have some updates for Twitter. So we have a little bit more information about the Twitter hack, the compromise of accounts in the compromise of accounts in for verified accounts that were used to perpetuate a cryptocurrency scam. So it turns out that this was social engineering, just like we thought. And it was masterminded, if you want to use that term, by a 17-year-old kid from Florida, which certain security industry experts kind of saw coming, particularly Rachel Toback, who is a social engineering expert. You may have seen her on CNN. Kind of called it when the hacks started that it was probably going to be a kid, and that tracks with a lot of things that we knew. Apparently, some of the DMs sent were kind of like, "Hey, you're hot. Add me on Snapchat." So it was definitely something that seemed like it was a young boy doing something. And also, you know, the scale of the compromise versus what was done with it just did not track. And I think this makes a lot more sense that it was in fact a kid who did it. A couple things. First of all, the 17-year-old is being tried as an adult. We could decide whether or not that's a great idea, but there were also three others. So four people have been charged so far, and one of them is 19, so he's facing quite a bit of time in prison. Something to keep in mind as we go through this cybersecurity material, that you really do have to stay on the right side of the law. Even if you know, I think a lot of times when people get into hacking, they start idolizing things like anonymous or hacktivism, right? This wasn't that. This was just crime. But even if you do idolize people who are hacking for good, you're still breaking the law, and so that's not really the way we want to go here. You want to use your cyber skills to improve people's lives, and ultimately, my position is that you can't really do that if you're breaking the law. The other takeaway that we kind of knew, but now we definitely know from the Twitter story, is that social engineering works. It is not considered by some to be like the most technical of attack vectors for an organization, but it works. And it's something that we really have to be aware of, something that we have to protect against. And how do you protect against social engineering? Well, you have to train people to be vigilant. You have to train people to pay attention to requests that are being made of them. Watch for appeals to authority, right? If somebody's claiming to be in a position of power over you and asking you to do something because of that power, that's an appeal to authority. Urgency, if there's if something is an emergency, you have to do something right now. It's like, hey, my car had a flat tire. Can you send me some money or something like that? And then sympathy. Social engineers prey on people's desire to help other people, right? They prey on your goodness and your charity. They will take advantage of that to get what they want. So you got to be aware of those appeals when you're dealing with interactions from sources you're unfamiliar with. And that training has to happen for everybody in an organization. And it doesn't matter how big, how small, social engineering attacks happen everywhere. And if it happened to Twitter, it can definitely happen to you. We had another cool story that broke. I don't know if it broke this week. I think it broke actually late last week, but this was about Blackbaud. Now, if you're not familiar with Blackbaud, they are a technology company that specializes in software and services for nonprofits. If you're not from the United States, not-for-profits are organizations that are charitable in nature, that they exist. They produce revenue, but they don't distribute it to shareholders, and their they perform some sort of public good. They're also tax exempt. So they're a specific kind of legal entity in the United States. And one of the things that is tricky about running a nonprofit is that you have to manage your donors. You have to keep really good records about your donations, not only for auditing purposes, but you want to track donors. You want to keep in touch with them. You are going to want to ask them for more money. Okay, so this software that Blackbaud produces that kind of rules the roost when it comes to this market, they definitely have a monopoly, is called Razor's Edge. And it's been around for a long time, and they serve nonprofits, they serve schools. They also offer other products to schools in particular that I'm familiar with, having worked in education, to do things like set up your learning management system and provide homework. They've been seeing some good business since everyone's at home doing schoolwork. And managing report cards, things like that. So they have this suite of software that they offer, and nonprofits are a tempting target because if you're donating to a nonprofit, you have money. So somebody went after Blackbaud, and they executed a successful ransomware attack against Blackbaud. There are a couple of things about this attack. It wasn't super technically interesting, but the way that Blackbaud responded to it, I think, is instructive in that they responded to it terribly. First of all, they paid the ransom. That's always a dodgy situation. You want to be in a position to not have to. You should have backups that are isolated such that an encryption of your data, your live data, is not impacted too badly and you can recover quickly. That wasn't the case here. Now, the data that was compromised was customer data from Blackbaud, which included, as they claim, aggregated anonymized donor data from certain organizations. Now, that's sensitive. It could have been worse if that's all that was actually exfiltrated. And remember, with ransomware, what we're seeing these days is this double dip attack where you have the data encrypted and it's exfiltrated, and then if you don't pay, the ransomers will threaten to leak it, or they'll just leak it anyway because they're criminals. They don't, there's no code of honor here. And the way this was communicated to Blackbaud's customers was very vague. It took some time for it to happen, and they also kind of trusted the ransomers to delete the data. They didn't require any proof that actually occurred. So a little bit tricky there. And then, of course, it became incumbent upon all of the individual organizations who had contracts with Blackbaud, had accounts with Blackbaud, to notify their donors, their communities. So there are a lot of moving parts here, and it's just a great example of what not to do for a ransomware disclosure. Lastly, in cyber news, there was a really cool vulnerability that came out this week called Boothole. Boothole is a vulnerability in a part of the computer system that we haven't talked about yet. It actually comes in kind of before the operating system when you're turning on your computer. So you turn on your computer looks it used to be called the BIOS, but now it's called the EFI, extensible firmware. But the idea is that the kind of close to the metal hardware is looking around for an operating system to boot. That's the basic idea, and it's looking for storage devices like hard drives that can boot, and it looks for one and finds one. In part because of a partition called an EFI partition, but the thing that the data that is stored on that partition is called a bootloader. Okay, that bootloader handles the startup process of loading the operating system into memory so that you can actually use your computer. All right, with that out of the way, there was a vulnerability found in the bootloader that Linux uses called grub. And long story short, it would allow for an attacker who already had a lot of privileged access to a device, but would allow an attacker to load like a compromised operating system or add code into the base of the system without really anybody being the wiser, including onboard antivirus or anti-malware. Because if the operating system is compromised, you're kind of SOL right from the start. So really technically interesting vulnerability. And in terms of severity, I mean, it's bad because of what can happen, but because you already need to have privileged access to a computer in order to exploit this vulnerability, it wasn't, the most scary thing that had all of the administrators across America and across the world, rushing to patch. In fact, they can't patch yet, and this is why it's also interesting. So in order for this to be fixed, there has to be this coordination between many, many groups. First, the fix has to be patched in the Grub bootloader. That's one. Then the patch has to be tested on a whole bunch of different systems, different kinds of hardware, because if the bootloader doesn't work and you install it, that's the ball game for your system, especially an embedded system like a firewall or router that you can't boot any other way. So if you mess up the bootloader, that's it. That's one. Two, you have to, so that has to be tested. Then, Microsoft, who actually has some responsibility for signing the bootloaders to verify that they are correct, has to add new signatures, or add new verification signatures for the new versions of the bootloader and revoke the old ones. But here's the trick. If Microsoft revokes the signatures for the old versions of the bootloader before the new version is patched, every computer that has the old version of the bootloader will be bricked, right? You won't be able to boot it anymore. So there are a whole bunch of moving parts, and it's going to take months to remediate. So just thought it was kind of interesting that, this vulnerability, once discovered, kind of kicks off this whole chain of remediations that involves everybody from the developers of the bootloader to Microsoft to system administrators worldwide. All right. That's it for cyber news this week. Hopefully we'll have some more stories. Hopefully you're enjoying this part of the pre-show. I'm enjoying getting to talk about some of these stories with you. All right, but with that, let's get started. Welcome to Hack Summer. My name is Taggart. You can find me on Twitter here at mttaggart. And just before we get going, quick favor, if you are enjoying what we're doing here, if it wouldn't be out of your way, please go ahead and like and subscribe to the channel. It helps other people see these videos and take advantage of them. I don't love doing this stuff, but I don't love doing the self-promotion stuff. But if you could like and subscribe, I'd appreciate it. So what are we doing here? We are looking at Python. We are looking at cybersecurity. And we're starting from scratch, going piece by piece, building up our understanding of these topics. Now, last time we kind of went out of our way to explore a little bit beyond the boundaries of just Python, and we explored the operating system on which our Python code runs. We did that by spawning a bash shell by way of Python using the PTY library, and then we explored some shell commands. The command from the Linux command line interface. We did ls, we did cat, we did grep, and we learned about output redirection, how we can take output from these commands and send them to files if we want to. And we also learned how to use the sys library to send information to a Python script with sys.argv so that we could create real command line applications. So we're going to come back just a minute. We're not going to go down the command line path anymore right now. We're going to recenter on Python for this week. And we're going to talk about a data type that we haven't explored yet, but is absolutely essential to our understanding of Python and the way that we're going to build applications. And that data type is dictionaries. Now, we've used lists, and dictionaries are a sequence, but they are more structured than lists or tuples, which we have seen. And we're not talking about dictionaries like this, really, but keep that image in mind because it actually does relate. So let's imagine that you have a very large list, and you're looking for something in it, and you don't know exactly where it is, what index it is. How would you find it? Well, and let's imagine the worst case scenario, right? That is at the very end of the list. How would you find it? Well, we know that there is a .index method on lists, right? If you have a list, you can use the index method and it'll return the index, the first index that matches the element that you are looking for. But how does that work? How does that index method work? It's literally just looping through. It's flipping through the list and looking at each one. So imagine like a deck of cards, right? And you have to find the right card. Worst case scenario is, if you're looking at each card in turn, the card that you're looking for is at the very bottom. Okay, well that sucks, right? You don't want to have to look through the whole list. If only there were some other way of relating information. So if you know a piece, if you know what you're looking for, what if there were an easier way to get to that thing that you're trying to reference? And that's what dictionaries do. And that's why this image is really, really useful, I think. So you can see on the side of this dictionary here that there are these indentations. Does anybody even use dictionaries anymore? I don't know. I grew up with books, so this was a thing for me. But you look at the side of these pages, and there are these indentations that will tell you what letter you would be on if you flipped to that page, right? And it was really, really helpful. Rather than having to flip through the whole dictionary, you could cut right to the letter that you needed, or in between the two letters if you needed to go in between. So with dictionaries, what we get essentially is a reference like that for every single element in the dictionary. So we can look things up by reference. It's relational data rather than just a raw unstructured sequence. What we're going to do is we're going to create a set of usernames and passwords, and we're going to do it first with lists, and we're going to do it with dictionaries. And not only are we going to learn the syntax of dictionaries, but we're also going to learn how to test for speed. So we're going to learn a little bit about benchmarking. Let's get started. Okay, so I'm over here in Replit, and the reason that I'm not already in the code is because I wanted to show you kind of a new way that we're going to start off our REPLs here. Instead of starting with a Python REPL, I'm actually going to start with a Bash REPL. So if you search for language in Bash, you'll find it. It kind of looks like our terminal prompt in a cube. And let's call it, I'm going to call mine a dict demo. You can call yours whatever you want. But let's go ahead and go into the Bash instance of Replit. Now, it at the beginning doesn't really look that different, right? We have the main.sh, and we have, which is a Bash shell script, which we're not going to play with, okay? And we're actually never going to type. We're not going to click run. We're never going to do that. The reason I wanted to go into the Bash version of this is because we're going to type Bash over here on the right-hand side, press enter, and check it out. We have a shell very much like what we had last time, although it didn't require us to import PTY, okay? Or do any of the other stuff. We're not escaping Python first. So this is actually a little bit of a more effective way of getting to the kind of interface that we want. Just to confirm that we do have Python on this Replit, let's go ahead and run python -- version, and tells us that 3a3 is installed, which is great. That's what we need. And sure enough, if I type Python, right, it'll actually take me into a Python shell, right? And I can do stuff like print hello world. And it'll work, right? I have access to Python that way. Exit, by the way, as a function with our parentheses to exit out of that. But I have an actual shell here, and that's going to be useful. Okay, so how do I write Python code if I'm doing Bash? Well, the first thing I'm going to do is going to make my Python file. So to do that, I'm going to touch. Let's do dictdemo.py. And you can see that as soon as I did that, an empty file was created in the folder that I'm in. The Replit interface found it and shows it to me here. But of course, I could also list the contents of the directory with ls, and it'll show it there as well. All right, let's click over into the dicdemo.py and just to show, print, it is highlighting Python syntax. It recognizes it as a Python file. So I have the ability to work in Python, even though it's a bash REPL. Okay, so what we're going to do first is we want to make a set of usernames and passwords and look up a username, look up a password based on a username. And we want to do it first with lists, and then we want to do it with dictionaries. And we want to test the speed difference. So how do we do that? The first thing we're going to do is to test the speed difference, we need time. So let's import the time library. Impoti, great. Off to a good start with the typing. Import time. So the time library has a lot of cool methods that we can use, but time.time will return the current time. So let's just go ahead and print that. Now remember, we can't use the run button, right? Because run is kind of baked into the REPL, the replit interface. In this case, it would run the main.sh, and I don't want to do that. I could hack it to say do like Python. We'll do that in a second, but first let's do it this way. So to run the dicdemo.py, what I want to do is come over here and say Python dicdemo.py. That tells the Python interpreter on the computer to execute this Python script. Okay. What is this? This is what we call an epoch, EPOCH time. And it is that on here? No. Yeah. Date on here? Yeah. So basically it is the number of, in this case, I believe milliseconds since milliseconds? Pretty sure. Maybe seconds. I always forget how Python does this. But pretty sure it's milliseconds since January 1st, 1970 at midnight. That's kind of when time started for computers. So that's what we're looking at, and what we can do is we can actually use the difference. We can add and subtract times. So let's say then equals time.time, which will capture the time at that very moment. And we'll say now equals time.time, and then we'll print now, the difference between now minus then, and just to see how quickly that happens. Again, I keep wanting to go to the run. If you want to do that, if you want to reconfigure Replit so that the run button actually works, all you'd have to do is go over to main.sh, right, and tell it to run Python dicdemo.py. The problem is that when you do that, you're going to lose your shell that looks cool like this, and it'll still work. But so watch what happens if I hit run, right? You can see that it runs that thing, and then I get this back. So okay, so 9.5 times 10 to the 7th. So let's see. So 9.5. So 9.5 times 10 to the 7th. So let's go 1, 2, 3, 4, 5, 6, 7. So it took that many seconds to execute. Cool, right? So that's how we can use time to do a speed test. I'm gonna get back into my nice bash shell because I prefer to do it this way. But if you did want to click the run button, that's how you do it. Okay, so we know how time works now. Well, in the context of Python. Now let's go ahead and make our logins in list form first. So I'm going to make an empty list and line break it there. What I want to do, if I need to have a relationship between a username and password, how do I store that? I mean, I could do like all the odd elements. Like I could start with username, and then the next element would be password. And I could kind of do an even odd thing there. But that's really, really fragile. I don't want to do that. Instead, I'm going to do tuples, so a list of tuples. So here I'm going to have a list, and inside of it, each element is a tuple. So let's make some usernames and passwords. I'm going to stick with Trek, and let's see, what was Jean-Luc Picard's? This is username, and his password would probably be something Shakespearean, like Hamlet. All right, let's go for Riker. We know that Riker, whoops, so that's got to be inside the parentheses. Riker would choose Imzadi. For Troy, probably the names of her kids. And Data actually knows about cybersecurity, so he's going to choose a really hard, complicated password. It would probably be longer than that for Data, but I'm not an Android, so we're going to keep it that short. Okay. So we have our logins. We could maybe even say login list. Okay. Now let's, before we do any checking here, let's make the same, let's produce the same data, pun unintended, in a dictionary and see how it differs. So we'll do login dict equals, and then instead of square brackets, we're going to do curly braces. So same key, but with a shift, and line break. Now, dictionaries use what are called key value pairs. And this is a concept that you'll see time and again in programming, which is we'll have a key and then an associated value, which is why we call it relational data. So what we're going to do is create a key for card, colon, and then the password. Okay. Then comma to separate the key value pairs. So Riker, same thing. Pay close attention to the syntax here, right? That we've got that colon between the Troid. Great. We have a colon between the key and the value, and we have a comma separating each key value pair. And we'll do data. I'm not retyping that. I'm just going to copy it. Okay, so we have a login list and we have a login dictionary. Let's think about how we would look up a login with a list. And let's write that as a function. Call it list lookup. That should be 2 words, list lookup. And list lookup is going to take 2 arguments. The first is going to be the list that we're going to be searching through. I'm doing it as LST because list is the word list is a reserved keyword in Python, so I can't use it. So LST. Comma, and then query, right? Whatever the query is, whether it's Picard or Riker or whatever. That's going to be the string that is what we're searching for. So again, think data types. We have a list coming in here, and we have a string that we're looking for in here. All right. Now, all we have is a list of tuples, right? We have a list of these things that are paired username and password. So I got to look through the whole thing to find what I'm looking for. So if I have to look through the whole thing, that's going to be a for loop. For L in list, or LST. What are we going to do? We have to search, we have to check if the username matches, right? So if, now remember that each element in the list is a tuple, which itself is indexed, right? Index 0 of the tuple is the username and index 1 is the password. So I'm going to check for the username. If L0 equals the query, then we're going to return the password, which is L0. 1. Now, let's say we get all the way to the end of the list and we don't find anything. This is one of those situations where you actually might want to return a different data type. In this case, we're going to return something called the none type, which is just, yeah, we didn't find anything. This is actually, this is an appropriate way to do it in Python, but it's actually something I don't love about Python, which is that it encourages you to have a different return type. But that's a little in the weeds. Big picture, if we find it, we return the thing. Otherwise, we return none. Okay, let's just confirm that that works. How do we do that? Well, over here in my shell, I'm actually going to kick off my Python interpreter. And then I'm going to say from dict demo, because it's in the same folder, I can do this, import everything, asterisk. This is really, really cool. So check it out. I have login list, right? It's there. And I have the login dictionary. And I also have the function list lookup. So what I'm going to do is I'm going to call list lookup with the login list as the list, and let's look for Troy. So great, the function works. Very happy about that. Let's exit out of our interpreter. And now we're back at the regular shell. Let's try to do the same thing. Let's see how we would do it for a dictionary. So in this case, we're going to do def dict lookup. And we're going to say DCT, because again, just like list, dict is a reserved word in Python, so DCT, and that'll also take a query. Okay, so now we have a different kind of thing coming in. We have a dictionary. With dictionaries, actually, let me go back over into the Python interpreter and re-import dict demo. Oh, whoops, can't do that because let me write pass here, which is saying I haven't written this yet. There we go. So we have login dict available to us here. Okay, to look up a specific element in a dictionary, we use the key. And we do it the same way that we do indexing with lists or tuples or strings, right? Any other sequence. So what we would do is say login dict, square braces, and then the key, in this case, Picard, right? And the square braces, and it'll return the value. So that's how we get to stuff in a dictionary. Now let's see what happens if the key isn't in there. So let's say Jordy, right? We get this key error, and that's going to be important. Okay, so we just go to it with this. We don't have to search, right? We just go to it. But we do have to account for this error. So let's come back over to our dict lookup function. There's not much to do with the lookup, right? Basically, if the query is there, we're just going to say return the value found at that key. Right? That's kind of it. But we do have a problem where we want to be able to handle that error without the program crashing, right? Because you could look up something that isn't in there. So what do we do with that? There is another structure that we want to begin using, which is the try and except structure. So what we're going to do is we're going to wrap this return in a try, colon, and then indent it. That tells Python, hey, give this a shot. But if it doesn't work, we're going to give it what to do in the event of an exception. Now, you can write it this way with just any exception, or you can specify an error And you can have different kinds of accepts for different kinds of errors. In this case, we'll say accept key error, but you could also just write it as a raw accept. So accept key error, meaning, okay, that means that the thing you were looking for wasn't there. Let's return none. Well, that looks good. I have to exit out of my interpreter and go back in order to re-import my code. But let's try this now. So dict lookup with the dictionary, which is login dict. And the query, let's do data. All right, so it works for elements that are in there. Let's try it for things that are not, like crusher. Okay, it just returns none. So it doesn't crash. You could handle it other ways. You could say print, username not found or something else like that before the return. But basically we have our structure here. So we have a working function to look up usernames in a dictionary, and we have one for doing it in a list. Now, let's race them. Let's see how fast each one of them is. Now to do that, we could write, let's think about what we would have to do in order to write the time test function. What do we want to do? We want to take the function, run it, and see the difference in time between the start and the end. Now we could write a different test function for the list lookup and the dict lookup, but it turns out that you can send functions as arguments in functions. So that's going to probably mess with your head for a second. What I'm saying is that we can actually write a single function here called time test that will accept either list lookup or dict lookup as something we send into it to test. So we don't have to write a different testing function for both of these. We can just write one. The first argument to time test is going to be the function itself, and then we're going to ask for the we'll call it the SEQ, the sequence, whether it's a dictionary or a list, and then we're going to ask for the query. So we'll be able to send these arguments onward to either list lookup or dict lookup from the time test. All right, we have to find out when we have to press the start button on the stopwatch. So we'll say start equals time.time, capture the time at that moment. And then we can say end equals time.time. And what do we do in between? We're going to run the function. Now, we don't, because we're sending either list lookup or dict lookup into time test, and we're naming that argument fn here, we're actually going to say fn. That's the function we're calling, and we're calling it with the sequence and the query, whatever it is. Okay, and then we'll say runtime, total runtime, is equal to end minus start, and then we return it. We return runtime. Okay. Let's, I keep wanting to click that run button. Let's restart the Python interpreter just to play with this. By the way, very soon I'm going to show you a way to work in this method without having to constantly restart the Python interpreter. We just haven't covered it yet. There is a way to do it. Okay, so we're going to do the same thing from dict demo, import everything. So let's run the time test for the function list lookup. Let's give it, notice that I'm not using parentheses here. I'm not calling the function here. I'm just sending the function onward as an argument. Then I'm going to give it the login list as its sequence. And then the third argument is going to be the query. And let's make it kind of middle. Let's give it Troy. Okay, it took 3.8 times 10 to the negative 6th seconds to make that happen. That's pretty fast, objectively speaking, but let's see what happens when we run time test with the dictionary. Let's say list, let's call it dict lookup, right? That's the name of that function. We change login list to login dict, and let's run this. Now, that one wasn't that much faster. It's really interesting, but it was a little bit faster. 3.099 to 3.8. Let's try the worst case scenario for login list, which would be looking for data. That took 4.29. Now let's try the same thing with the dictionary. Okay, 2.38. A really important point that I want to drive home here is that this worst case scenario, right? The bigger your list is, the bigger the difference in this time is going to be. So when you have a situation where you're going to have to reference data like this, reference data literally, you probably want to use a dictionary, because the structured nature of it and the ability to look things up like that, being able to cut to the exact page, is really, really valuable. Now, it takes a little bit more space, but we have plenty of space. And sometimes we want things to be faster. And in this case, it was almost twice as fast. All right. So there is our dictionary demonstration. And we've learned about how fast they are. All right. Before we move on, I want to talk a little bit about the philosophy of what we're doing next, which is I don't always love teaching with games. And in part, it's because game development is a million skills, right? It's not just programming. And what I see a lot of times when folks start with programming in games or learning programming through games, things like Scratch, is that, it's definitely worth doing and worth exploring, but students will often get distracted by the decorations, right? Creating cool looking characters or the gameplay. And those are good things to learn. But we're doing programming, right? I want to make sure that you understand the logic of programming. And so sometimes games are a distraction from that. That being said, I'm definitely going to use a game to teach you about dictionaries, because rock, paper, scissors plays really well into this. So just in case we have somebody who's not, I don't know how global rock, paper, scissors is, right? So just in case we have somebody watching who isn't familiar with the rules of rock, paper, scissors, here's the deal. Rock, paper, scissors. And it's a triangle of supersedence. So you have two people, right, who play, and they go like rock, paper, scissors, 1, 2, 3, shoot. And so rock beats scissors, right, because the rock can break the scissors, and then paper would beat rock because it covers the rock. It's dumb, but whatever. And then scissors, of course, beats paper because the scissors can cut the paper. There's like an older one that I learned in school, which is like earth, fire, water, but same kind of idea. Anyway, this sort of rule set is really easy to describe with a dictionary. And so what we're going to do is we're going to make a rock, paper, scissors game, and we're going to encode the rules of the game with a dictionary. And we are also going to set up a high score function, hopefully, if we get to it. I think we have time. And we're going to, we're going to put the whole thing together so that you can play rock, paper, scissors against the computer. Now, before we get started programming, this is one of those things where we really want to think through what we have to define. So we're going to start by thinking about the order of play and also the different pieces of the program that are necessary before we jump in and write a bunch of code. And this is where good structured comments are really going to help us in our code too. All right, let's head back over into Replit and get started. All right, so I'm going to make a new replit or new REPL. And same thing, I'm going to do it in Bash. And actually, because of what we're going to do with the high scores, this is going to matter even more. So you could do it in Python. I really encourage you to just follow along and use a new Bash REPL. And we'll call it RPS. Okay, same sort of deal. Let's go ahead and set up our environment. So I'm going to type bash to get over into my real shell. And then I'm going to touch rps.py. All right. And then just as a safety measure, just in case you do click that run button, as I've almost done a bunch of times, let's modify the main.sh, which is what will run if you click this, to run rps.py with Python. So Python rps.py. So if you do happen to hit the run button, it'll still run the program, no problem. And come on over to rps.py. Let's think about what we need to do. So the order of play. Let's think first about, I'm going to do this in a multi-line comment as we think through this. Okay, so order of play. The first thing that's going to happen is, and this is just in a game, right? A single game of rock, paper, scissors, is the player has to choose rock, paper, or scissors, right? Now, there is a possibility we have to handle where they try to get cute and don't choose rock, paper, or scissors. But good news, we just learned try and accept. So we have a way of handling that. There are actually some other ways to handle that too. Okay, player chooses rock, paper, scissors. Now, if we were playing against another human being, the opponent would have to choose the same from the same set, rock, paper, scissors. But we're going to play against the computer, so the computer is going to choose. Now we're just going to we're going to use random like we did before for what did we use random for? I don't remember exactly, but we used random before to create to pull like a random for our password generator. That's what it was. So we're going to use random to choose randomly from rock, paper, or scissors, and then we have to compare the choices. So what does that even look like? So rock beats scissors, right? So, and then paper beats rock and scissors beats paper. So we have to encode this somehow and then determine who won. There are three possibilities, right? There are three possibilities. Either the player won, the player lost, or the player and the computer tied. And then we're going to keep score. So that's the order of play. And we want to write the game in such a way that you can actually play more than one game of rock, paper, scissors. That would suck, right? If you just run the program and then it stops. We want to write it so that you can keep playing. So just from there, we know that a few things that we need. The first thing we need is the rules of the game. Now, I'm going to, if we were in a classroom together, we would have a good discussion about how to define the rules of the game. And if you want to think about it, I really encourage you pause the video here if you're not joining us live, and think about it. How would you encode the rules of the game? How could you do it with the tools that you have at your disposal? Think it through, give it a try, and then come back. Or if you're with us, or you just came back to the video, here's how I think we might want to do it using dictionaries. So let's take advantage of dictionaries, and let's create a key value pair set called beats. And I promise this will make sense once we get going. So let's make the key one of the items, rock, paper, scissors, and the value, the thing that it beats. So we know that rock beats scissors. We know that paper beats rock. And we know that scissors beats paper. Why is this cool? This is cool because if I ask for beats and then the index or the key related to, say, the player choice, it returns what it beats. So I can check very easily whether the player choice beats the computer choice, or vice versa, or if they tied. So this is a really easy way to encode this information, and I think you'll see that as we write out the rest. Now let's write. The first thing I want to write before we do anything else is a helper function for printing the choices that we have. So let's write print choices. Doesn't need anything, but it is a function, so empty parens and then a colon. And this is also, some of these functions that we're going to write, the helper functions for printing, are going to break the rule about not returning anything. So we're going to print, and we're going to print choose one, tunes, good job. And then we have to loop through beats. Now, something really interesting is that when you do a for loop against a dictionary, what you end up looping through are the keys. Okay, so if I were to say for B in beats, B is going to be in turn rock, paper, then scissors, which is really handy because that means I can just print B in this case, right? Print B. And I'm also going to add something to the beginning of my choose one. There's going to be a lot of text that goes down the shell as we run the game. And to provide a little bit of visual separation between lines of text, we're going to add a line break. There are a couple of ways to do that. I could just like print nothing like that. That would do a line break because print adds a line break at the end of everything it prints. But I can also use an escaped line break character, which is backslash. That's on American keyboards, that's the key above the enter key. It's the top left to bottom right slash. That's a backslash. Anyone who tells you that this is a backslash is wrong. They're a forward slash, and I'm sorry to be pedantic about it, but words have meanings. Backslash n, and check it out. It changes color because Python's recognizing that as an escaped string. And so that's a line break. So it's going to go down a line before printing choose one. Okay, so we have print choices. And let's write a few other helper functions, just even based on what we know we need here. So what we say, player chooses rock, paper, scissors. We got the choice down, but how do we get the choice? Let's get the choice. Just player choice. I don't need more than one. So we're going to do def get player choice. And we say choice equals input choose, just like that. We could also add a line break at the beginning of it if we wanted to. You could even say, you know, nicer, like your choice. And let's do that. Let's add a line break at the beginning of that just to make it a little bit cleaner. And then return choice. Now, you can do this in one line, right? You don't need this variable, right? This choice variable. Don't need it, right? You can just return the input of this. That's fine. And that's actually what we're going to do. I want us to get into the habit of being able to make our functions elegant whenever possible. Now, there are ways of writing functions that are really elegant in code but are unreadable by humans, and we want to avoid that. But that's not the case here. This makes sense. And it's basically a one-liner function. But and we didn't have to write this as a function, but I like breaking things down this way because it makes each piece easier to test. And when we finally write the main game loop, it's going to be so clean. It's going to be so much cleaner to read. Let's do get computer choice. Now, for this one, we did import random, right? Oh, no, we didn't. We need to do that. At the very top, we need the random library. So let's go import random at the very top. Now we'll have access to our random methods. Something that we need to know about dictionaries is that they have a few built-in methods. And let's actually go over to the Python documentation for this. We're going to go docs.python.org, library reference, and then we're going to, dict is technically a mapping type, not a sequence, but I think it's technically a piece of a type of sequence anyway. But okay, so key value pairs, that's what a dict is. If we go down, you can see it has a lot of the same abilities that we have from lists. Okay. It also has a built-in method called keys. And that just returns a new, it calls a new view of the dictionary's keys, which we'll deal with. But essentially what it does is it gives us the ability to just extract the keys rather than the values. And that's kind of what we want for the choices, right? Because we have the choices in rock, paper, scissors, right? So I just need those. What do I need? Because remember that random.choice takes a sequence. Well, I need a sequence. Okay, well, random.choice, if I give it beats.keys, that's actually not going to work because of the data type that .keys will return. It's kind of annoying. It's just a Python idiosyncrasy that they have introduced recently. It didn't used to be this way. But so what we want to do actually is say choices equals beats.keys, but we're actually going to wrap that in a type conversion to a list. And technically, you could absolutely have just put that down here, but that's harder to read. So random.choice choices. And we need to return that. All right, that's pretty much it for getting the computer choice anyway. All right, getting there, we have some of our pieces. And this, by the way, is a really different way of thinking about building a program, right? We're building the small pieces that we need first rather than kind of doing the big thing first. And there's value in doing it this way, which is that as you go, you can start thinking about how your pieces are going to work together. And you have a lot more control over the small details when you're working it this way. And then I promise that when we get to writing the big piece, it's going to look so much better, and it'll make so much more sense once we do it. So let's write our compare function. We have to compare the computer choice with the player choices. The player choice. In this case, I actually do want it to be plural. Okay, def compare. It's going to take player choice and computer choice. And here's where we have to do our comparison. And this is, again, where that beats reference that we talked about here makes so much sense. There are three possibilities, right? We talked about that. The three possibilities are win, loss, or tie. What does a win look like? The win looks like that if we look up player choice in beats, it equals the computer choice. That's what a win looks like. So let's test for that. If beats player choice is equal to whatever the computer choice was, then we'll return, in this case, we're going to return a string win, but you could do it numerically. You'd be like 1, 0, or -1, like 1 for a win, 0 for a tie, -1 for a loss if you wanted. But we're going to do it this way. Do return win, just to make it clear. Okay, second possibility. The unthinkable has happened, and we've lost to the computer. That would look like the computer choice in beats being equivalent to the player choice. Okay. There's one other possibility, which is the tie. Now, because there's only one other possibility, we don't have to do another elif, we don't have to test for the condition. It's win, loss, or tie. We've already tested for win, we've already tested for loss, so else it is. Return tie. There's our comparison function. Okay. With that, we are ready to write the game loop. So let's come down here to the very bottom of the screen, and let's write the game loop. Now, I've left something off here pretty important, but you'll notice it when we start writing the game loop. Now, remember that we want the player to be able to play as many games of rock, paper, scissors as they want. To do that, we have to actually create an infinite loop. We don't always like to do that in programming, but we actually do want to in this case. By the way, we're coming up to the end of the hour, and we are going to go over. Seems like people are sticking around, so I think it's worthwhile to just get the lesson done. So just a heads up, we will not be done at 11 Pacific. If you have other places to be, that's okay. Certainly stop back and finish the video. But yeah, we're going to keep going until this is done. Shouldn't be too much over, but wanted to call that out. Let's write this game loop. So we're going to write an infinite loop while true. True is always going to be true, so this loop will never stop unless we manually break it. So the first thing we're going to do, remember, here's our order of play. This is why this mattered so much. In fact, we could even take this order of play comment and put it inside the function. Helps us keep track of what we're doing. So while true, we're going to do the print. We're going to print the choices. This is why, again, so handy to do it this way. And then player choice equals get player choice. How handy is that? Now we have to do a couple of things. The first thing we need to do is make sure that the player chose something valuable, meaning valuable, valid. So we have to say if player choice is in beats.keys. Again, remember we're getting the key values. Actually, let me test something real quick. I just want to test to see if I need to do the dot keys for this. Paper, beats, rock. And I'm not going to finish it. I just wanted to test this. Rock in RPS. Yep, I don't have to. If I do the in keyword, it'll look for the keys without me having to look for beats.keys. So that's what I was checking. I don't remember everything. I just know how to look stuff up. So we don't have to do this dot keys for this one. We can just check this way. If player choice in beats, that'll work fine for us. So if it is a valid choice, then we're going to go off and do our stuff, right? So we'll say computer choice equals get computer choice. And we'll even say, we can even say print computer chose. And remember that format thing that we did before with the curly braces for putting strings inside of, or putting data inside of strings. We'll do that with that. So we're printing out that the computer chose there. And let's also put one of those nice line breaks before and after this, just to make it nice and clean. And then we'll say result equals compare. And we're going to do player choice and computer choice. And then we're going to have another conditional to handle win, loss, or tie. But we're not there yet. Let's come back out a level. Let's put a comment here for us that we're going to handle the result. But let's come back out. Let's say, what do we do if the player choice isn't in beats? What do we do if it's not? We're going to say else print, and then do that new line thing again. Not a choice. And because we're inside this infinite loop, it'll say not a choice and then come back again and print the choices again. Now, this is going to work kind of, but we have a problem. Let's actually look at it. So let's do since I have the Python interpreter over here, and if you needed to get into it, remember we do Python from the command line, from RPS import asterisk. That imports everything. So I have beats in there, right? But I also have the game loop. So let's call the game loop. So I've got choose one, rock, paper, scissors. If I do rock, it'll like go and do stuff, like says computer chose scissors, and then nothing happens because I haven't handled the result yet. But if I choose something like shotgun, it says not a choice, and then I come back and I have to choose again. How do I stop? What if I want to stop? Well, I could do Control C, which like breaks the program, right? I get a keyboard interrupt, but that sucks. That's not the way we want to do this. So instead, we have to handle that some other way. To do that, when we go up to computer choices, or print choices, we're actually going to give the player another option, which is print press Q to quit. Okay. What that's going to do is inform the user that there's a way out. And furthermore, we're going to handle that possibility in this conditional tree. So we're getting the player choice. The first thing we're going to do right off the bat is check to see if they want to quit. So if player choice equals Q, break. We can be nicer about it. Also, we can say like print bye or good game or something, right? We say or thanks for playing, and then stop. But we want to stop. Okay. Actually, let's do good game in here. Okay, so we're handling the quit possibility. We're handling the not a choice possibility, which will bring us back up here to get the choices again, and they'll have to choose forever and ever and ever until they press Q. Now, let's handle the result. So we have the computer choice, we have the player choice, we've compared, we know whether it's a win, loss, or tie. Let's do something with it. For now, let's see. So if result is a win, print, again, we're going to do that new line, you win. Okay, and I'm just going to do a little copy pasta here, make this a little bit faster. And we're going to say LF result equals loss, say you lose. And then finally, else print it's a tie. Now we're not handling the score just yet, and that's by design, but we'll get there. Okay, we have the game loop, we have this working. Now you could, if you wanted to, take all of this and break it out into its own function called handle result. You can call it whatever you want, but I might call it handle result. And just take all of this, cut it out, put it up here, make sure the indentation is correct, which it is not at the moment. Whoa. Okay. And then why would you do that? You would do that because what you get for your trouble is down here a much cleaner game loop. Handle result and just pass the result off to it. And this is a stylistic difference. Other people may disagree. That's totally fine. I really like to write my functions this way. Meaning I like to build up pieces like this, and then when I get down to writing the main piece of the code that I need to do, or the main function, it's very clean, right? Minimum of conditionals, minimum of kind of branching flow. It's just function calls all the way down. And okay, we're handling the result. And for the moment, that works, but we have a problem, which is that we're not keeping score. We're not doing this last piece. Okay. Let's make the score. The score is going to be a dictionary that lives in here. So score is going to be wins, and it's initialized to 0. Losses, also initialized to 0. Ties, also initialized to 0. Now, we want to send the score off to the result. Why? Because we want to mess with the score. And we have to include that as an argument in the function. So if it wins, we're going to do, if the player wins, we're going to say score, and then we're going to look up the wins, and then we're going to add 1 plus equals 1. Do the same thing, except for losses. Sorry about the dog, if you can hear that. And do the same thing for ties. Let's also write a helper function to print the score. And give it a score argument to print. So again, we're going to do for k, meaning key, in score, kind of like what we did for print choices, right? And this one we're going to do a little bit differently. We're going to print a formatted string. So curly braces colon curly braces dot format k for the key, and then we're going to look up the value in the score dictionary with that k. So we're saying, okay, we know that when we loop through a dictionary, we get the key when we loop through it, but we actually have to go look up the value with that key. So this will say like wins 0, losses 0, ties 0 every time. And then let's print the score after we're done handling the result. Let's go ahead and run this, and we'll not run it from the interpreter. Let's do Python rps.py. But before we do that, we have to call the game loop down here. So call game loop like that, and then we can run it like so. Okay, choose one, rock, paper, scissors. Press Q to quit. Let's make sure that Q works. All right, it works. RPS.py, let's choose rock. Computer chose rock, it was a tie, and you can see that I got my score. Let's try paper this time. Another tie. Let's try, no, but check it out, something went wrong. This is really interesting. See how it still says ties 1? This is an important concept in programming, and I'm glad this happened, and I planned for it to happen. It's nice when a plan comes together. Let's try one more time. So let's try rock again. 3 ties. How lucky am I getting? Yeah, finally I lost. But look at what's going on. Do you see how it's like ties 1, and then when I lost, it went to losses 1? What's going on here? Here's what's going on. the score's getting reset every time. So this needs to be out here. And Replit has messed up my indentation, of course. Okay. Let's quit here and let's run it again. So now let's try this. Rock, I lost, there's one loss. Let's try paper. So now it's actually keeping score. Right, wins, losses, ties. And let's try scissors. And then if I just choose nonsense, it's not a choice. And then Q. I should probably print the final score. Before I end the game. So now we have a working rock, paper, scissors game. It seems like it's a lot, but that's because we're adding, more than basic features. And let's look at how we did this. We built up all the pieces. And then when we got to our final game loop, look at how little code there is, right? It's really not that much. And it's because we were able to take care of all the small pieces first. We understood what was going to go into making this game. All right. So I think what we're going to do is we're going to call it there. We're going to leave it there and pick up on this same project next time, because we have a few more things that we want to do with it. So, okay, let's talk a little bit about what we've done so far. So we have learned dictionaries, right? We've understood the value of key value pairs, how they can be more efficient than lists, and why you want to use them to store structured data. For example, usernames and passwords, or when we're keeping score when the score is more complex than just number of wins, right? Or just a raw number. We can look up the keys and get the values, so it's a little bit faster for large lookups. We've also started to build in our rock, paper, scissors game. We have 2 dictionaries, right? We have one for the rules of the game that we've encoded using a dictionary, and we have a score that is a dictionary. We're using good Python practice, building up small helper functions to write the full program, and we're getting user input and we're running the game. We even gave them an option to quit. Here's what we want to do next time. There are some features that we would like to add. So first of all, what if we could keep track of high scores? And what if we could save those high scores to a file? We're going to learn how to do that next time. And we're going to learn a little bit about something called data serialization and how we can use that for our high scores. And a little bit more structure to our program. From there, we're going to move on to some other features of Python. Again, we're going to do a little bit more game-based stuff. We're going to stay in Python for a little bit, and we're going to talk about classes or object-oriented programming. We'll talk about that next time, but this is a good start. Before we get out of here, I'd love for you to check out hope.net. Hackers on Planet Earth is still going on for a couple more days, and there's some great talks going on there. If you're interested in cybersecurity, it's definitely something to check out. A lot of really fascinating people doing things for Hope. Coming up soon, we also have DEF CON in safe mode. So if you don't have to travel to Vegas to check out one of the biggest, if not the biggest, security conference during the year. So just keep an eye out for that. I'll probably tweet out some more information about that. And then, of course, as always, if you're enjoying what we're doing here and you would like to give back, I encourage you to donate to Human IT. They are providing low-cost internet connections and computing devices for families in need. We're getting really close to the start of the next school year here in the United States, and it looks like a lot of places are not going to be in person. That's good news because we still have to do our part to reduce the spread of the coronavirus, but it does mean that families are going to continue to be strained in terms of their access to both networking bandwidth and computing devices to handle remote schooling. So anything you can do to help, either donate financially or old computing devices that they can take advantage of, they can refurbish and give to folks who need it, please donate at human-i-t.org. All right. So as I said, next week we're going to continue with our rock, paper, scissors game, add a little bit more finish to it, and then we're going to go into classes and class-based or object-oriented programming and how that can really help structure the way that we write our programs. All right, that's going to do it for this week on Hack Summer. Thank you so much for joining us.